the total. This is your ion beam coming here. This is electron beam coming here. This is that imaging camera, secondary electron detector, and so on. Yeah. Okay, so let's come back to our own cantilever and our own beam. It's the same video. If you want to see it again, you can see. Otherwise, you could go ahead. Yeah. Now the difference is in this model and this. When in a normal type of cantilever or film I hit from one side using steel balls or so, the size of that ball which is falling is quite large. It cannot go into the target material because in the target material, in this aluminium plate that is here, in this aluminium plate, the aluminium nuclei, they are at a separation of few angstroms. And this steel ball is 5 millimeters, so it just cannot enter. You don't have space where it can go. Therefore, it can deform the bond elastically. The bonds will be deformed, so some deformation in the material will be there, but the bonds will still be there. Okay, so it can come back elastic. Most of the time it is elastic, and if the energy is very high, it can rupture the whole thing. Right? So this is what happens if you have a macro size ball falling on a thin metal film. But here the particle size is small. That gallium ion itself is small, and once it goes to higher energy, it becomes smaller. You know that? A particle with 1 kinetic energy and a particle with 100 times more kinetic energy, same particle, the particles become smaller? No, not that length contraction. Not length, it's a de Broglie wavelength I am talking of. Okay? Higher the energy, higher the momentum, and the de Broglie wavelength goes as h by lambda is h by p. So that de Broglie wavelength reduces, and then this particle behaves as if it has that size of de Broglie wavelength. So what is there inside a proton? If you want to know what is there inside a proton, the technique is let electrons of some 500 mega electron volt kinetic energy fall on the particle, on the proton. Now 500 mega electron volt electron, the de Broglie wavelength becomes smaller than the size of the proton, and it enters into the proton, wanders and says that okay, there are 3 quarks in it. Right? But if you just bombard 10 MeV electrons, they will not be able to tell you what is there inside the proton, because the electrons, their own size is much larger than the proton size, so they will not know what is there inside. Okay, so these gallium ions, these energetic gallium ions can go in between the 2 aluminium atoms or whatever film is there. So it's not rupturing the whole thing, it's just breaking one bond and going in. And similarly, in that cascade area, it is making some more bond breakings and recoil and this and that. But the main structure is still there. That's the difference between the two. Yes? So what we have done first, wait. So we started with a silicon substrate, a big size silicon substrate. And in this big size silicon substrate, we have made this trench. 30 micrometer, 20 micrometer and 10 micrometer in depth. Okay, that was this part. That was this part. Correct. So we take a silicon substrate, and then using this FIB, we take out the material to make a trench of 30 micrometer, 20 micrometer, and 10 micrometer. So in between, I have this trench. Next thing is a thin metallic film. We have done with silver, we have done with gold, we have done with copper. A thin metallic film of about 200 nanometers was separately deposited onto a soap-coated glass substrate by thermal evaporation. So that metal is heated, thermally heated in some boat or something, and the substrate is put on the top like this. So the evaporated metal ions, they just go and sit on the surface. That's known as thermal deposition. So that is how this metallic film is deposited, 200 nanometer thickness, and the substrate was soap coated. Okay, why soap coated? Yes, next. Subsequently, this glass plate, so it is soap coated glass substrate. So this glass plate was cautiously submerged in deionized water. Right? This glass plate, this was the glass plate, and all this silver film was deposited from below, thermally evaporated, and this whole thing, this glass substrate and with this silver deposited, it was cautiously put in a water tank. And since it was soap coated, soap got dissolved, and this film just started floating on the water, and the substrate went down. So it was separated, the metallic film from the glass substrate, rendering a self-supporting film floating on the surface of the water. Then this floating film was carefully lifted and placed on top of silicon surface on which the trench was fabricated. So that film was lifted from that water tank, and on this silicon substrate in which we had made that trench, this film was just put there. Right? So this is that part. This is that part. It was just put there, and this became the starting material. Yes, and then we made this cuts. One cut here, and one cut here. So this part was the cantilever. Okay, this whole thing is that metal. This whole thing is that metal, and on that metal, below this metal you have trench, and then we made a cut using again FIB. We make a cut here, we make a cut here, we make a cut here. So that middle part, this middle part can come up and down, just like this. Right? This can come. So we made a cut here, we made a cut here, we made a cut here. So this was done. This, and then it was bombarded by the gallium ions from top. And as the gallium ions went on this cantilever, the cantilever came up. Yeah. So why did it come up? Because of the ion beam irradiation, white formation along with surface roughness occurs at the top surface. Right? When these gallium ions hit the top surface, white formation, vacancies formation, because the atoms are removed there, so you have gaps, and the surface also becomes rough. And so it creates, if the volume is decreased, you create some small gaps, some small vacancies, and surrounding your material, then this material will try to shrink. Right? You have a material, and if some vacancies are created here, and surrounding you have. So why this material is here? Because of that intermolecular attraction. So that attraction is still there. From here, the surrounding atoms are still in attractive mode. So they are trying to shrink. So compressive stress is developed on the top surface, not in the below, because the gallium ion could not go there. So the top surface, you have this compressive stress. It is trying to shrink. The bottom is still undisturbed. So that is what happened. So the surface atoms try to reconfigure themselves. As a result, compressive stress is developed at the top of the surface, and ion beam induced heating on the substrate. That also helps in this recrystallization process. So after this top surface is recrystallized, you have two kinds of layers. The top surface has different elastic properties because of all those stress and other things, and the bottom surface is different, and they are together, joined together. So that makes it bending like what we have studied, bilayers. You remember bilayers? Thermal expansion coefficients are different in a bilayer used in electric irons and other things, and it bends once it gets heated because of different thermal expansions. So similar kind of thing happens here. Okay, so that is the mechanism.